Welcome, and I'd like to present the speakers for session 3, which is titled Land Use and Ecosystem Impacts of Climate Change. The first speaker is Dr. Atul Jain. He is a professor in the Department of Atmospheric Sciences at the University of Illinois. His research focuses on understanding how interactions among climate systems alter the carbon cycle and to provide useful projections in global carbon and resultant future climate change. The title of the talk is Interactive and Cumulative Effects of Climate and Land Use Changes on Terrestrial Ecosystems. Dr. Jain?
Okay. Thank you. So let me give you a little bit background about my research interest. As has been mentioned, that I'm interested in interactions of climate with the biogeochemistry and also biogeophysics. And one of the components of my research interest is also the land cover land use change. Although it is a very diverse topic, there are a lot of dimensions of the land cover land use change. And today, actually, I'm not going to talk about most of this, the dimensions, but I'll try to focus on things which are important for this meeting, particularly about how the climate change is impacting the land cover land use change. But it will not be actually wise enough to just start with talking about how the humans have actually changed the land cover over the time and how they have impacted also the climate. And then there's a lot of interactions between, it's not worth just to talk about impacts of climate change. And also it's not so easy to actually identify the causes of land impact of climate change on land cover. So I have to be very careful about how to address these issues. So I have collected a lot of information based on my own research, but also based on the research I have done and on the literature. Couple of things. I'm not going to talk about, the agriculture, has already been discussed a lot. Today I'm going to focus more about the forest, because forest is also one of the important components of our Earth climate system. In fact, the forests are sequestering huge amount of carbon, but also they provide a lot of resources and how they are changing, and that's also very important to learn about, okay? So, as I have mentioned, that land cover land use change is one of the components of this Earth's climate system. When we talk about the terrestrial ecosystem, it is changing not because of the land cover land use change, because there are several environmental factors which are changing the terrestrial ecosystem. So it is all about the interactions, the cumulative effect, and it's very hard to identify what are the major causes of this terrestrial ecosystem, particularly the forest. Obviously, the humans are the major causes, but not only the causes. Climate is also another contributors. Not directly, but also indirectly. For example, forest fires are also happening. We have heard that ice is melting in Arctic and other regions. They are also impacting our plants, particularly the forest. So these are all factors. Also the atmospheric chemistry, for example, nitrogen is another component which is also impacting the forest. Fertilizers are also impacting the forest. We have heard a lot about the CO2 fertilization, but interaction of the CO2 with the nutrients makes a huge difference in terms of the forest and also the plant productivity. So I'm going to touch some of these issues today in my talk. So just to give you an idea about what I'm going to talk about, I'm going to briefly discuss about the historical land cover land use change. There I'm briefly going to talk about the crops and how the crops are changing over time, and also the forest. Then I'm going to talk about very briefly the impacts of land cover land use change on the biogeochemistry. That means how much are they releasing the carbon in the atmosphere. Not only the carbon, in fact, they release huge amount of other gases as well. On the biogeophysics, few slides. And then I'll come back and how these changes are impacting land cover land use. I mean to say biogeophysics, biogeochemistry, as well as the climate events, for example, forest fire and other the events related to the climate change. Okay. So first I will show you a few slides how the land has changed, particularly the crops. We know the crops area has expanded over the time. in our group, we have actually reconstructed the crop area over the last 250 years. And as you could see over the global scale, how the crop has expanded in a different regions. And that will tell you about, and the next slide, I will show you what is replacing, by these crops. So my starting year is 7070, and as you could see now, as the time is marching forward, starting at 7070, 1986, 70, the crops area is expanding, and particularly you look at the area in the US, and as you could see, the crop area has expanded from eastern part of the US to the Midwest. And in Europe, actually, it's other way around, from the western to the eastern part of the US. And it's not only about the human activities, as I will show you later. There are many, many other management practices and also the climate events, which are also actually helping to expand this crop area. And then next slide, I will show you how the forest has changed over the time, because most of the crops has been actually replaced as taking place on the forest land. So as you would see now, starting 7070, what has happened to the forest? And you would see the lot of forest is there in 7070, and it has changed over the time. And this is what you will see, that forest area is decreasing, particularly in the tropical regions, as well as in the high latitude as well. Not only because of the human activity, because of the forest fire. Particularly in this region, most of the forest is gone. There is no human activities, all because of the forest fire. So these are certain activities are happening over the globe and over the time. So what are the major causes of these changes? There are a number of drivers. We have heard a lot about socioeconomic drivers, population, and the economic drivers like GDP. And a lot of focus so far on this research has actually on these drivers. But then also the biogeophysical drivers. Nutrients are a very, very important drivers of the land cover land use change. I'll briefly show some of the work we have done on this issue. Then the temperature change, not directly the climate in terms of the temperature and precipitation, but indirectly, how they are changing our forests over the time. One other important thing which I also would like to mention, and I think it's worth mentioning here, and I'll just show you some of the results. Management also a very important role in understanding or changing, expanding the land cover land use. Another, regarding the management, it's very important that it's very hard to understand on a global scale. It's a very, very local phenomena, depending on the government policies or the local authorities, actually, how they are managing the land. It actually is worth looking. I'm just giving you an example. We did some research actually for India, and we look at the satellite data for the last 30 years, and we look at also the socioeconomic data, and we try to understand what is happening in India in terms of the land cover land use change, particularly what are the drivers of the land cover land use change. I just would like to focus one important, the research finding, which is related to the management. And this is the figure showing the drivers of the land cover land use change over the last 2 decades between 1985 and 1995. This figure is showing, and this figure is for the 1995 and 2005. What interesting in this figure is one area, this one, which is in fact actually seeing more cropland growing on underutilized land. It's all about the management. The government has provided more irrigation facilities to the farmers that is helping the farmers to grow more crops in this region. As you could see also in the later decade also that actually cropland has expanded. And in fact, it helps the government to control the deforestation, because now farmers, the government need not to actually deforest the land for cropland, and actually they can use underutilized lands to grow crops. So this is one of the examples of the management actually in fact actually helping the farmers to grow crops on underutilized land, at least in India. That's what is all about the management. Okay, now interesting thing about the interaction. So we have already seen the land cover land use changes are occurring over the time and on a global scale. And they have an impact on the biogeochemistry, carbon and nitrogen as well, and also the biogeophysics. But in return, they impact the land cover land use change. So it's not on the one way, the loop, it actually goes the other way. So once you have the CO2 increase in the climate, they impact the land cover. So I'm going to briefly touch about how the land cover is changing the CO2 in the climate, and also then vice versa, then these factors are impacting the land cover land use change. Okay, so first let's look at regarding this impact on biogeochemistry. So it's quite interesting that the land cover land use change is contributing about total amount of 25% of the greenhouse gas emissions. And this figure is from actually Working Group 3, IPCC Working Group 3. And what shows that total contribution of land to the greenhouse gas emissions. And this total bar is showing the total greenhouse gas contribution over this last 4 decades, 70s, 80s, 90s, and 2000s. And quite interestingly, that the contribution for land to the greenhouse gases is going down. And I'm going to discuss the why, but another interesting thing is, which I'm going to focus more about, that how the land cover land use change is contributing to the direct carbon emission due to the deforestation and the reforestation, and its contribution is, in the recent years, about 11% of the total greenhouse gas emissions. Okay, so now, another interesting thing is that deforestation is occurring and how they are impacting our climate. So I'm not going to go in more depth about this, but there is a quite interesting experiment on the paper published. And in that experiment, in fact, actually, it is done by the Hadley Center in England. And what they did actually, they deforested the land for the entire globe and then converted it into the grassland. And what this study suggests, how these actually drastic changes are going to occur in a larger scale, say, for example, northern high latitude to the tropics and then in the southern hemisphere, and how they are changing our climate, okay? So in the next figure, so again, there are, total area, forest area, which is shown in this figure, is converted to the grassland, and then how it is changing to the climate. So there are a number of factors which contribute to the climate when the forest is cleared. These factors, physical factors, are called albedo effect, which is shown in the first figure. Then the evapotranspiration effect, the forests actually evaporate more moisture, okay? And then the third one is roughness length, actually. It actually mixes the moisture in the lower atmosphere. And the fourth one is the total effect. So the forest actually, when the deforest occur in the higher latitude, the land is being exposed to the snow and all, and then it actually reflect more, radiation reach to the ground, back to the space. So it actually cools the environment. So when you deforest the land for the grassland, actually you have a cooling effect. And when you have a deforestation to the grassland, evaporation actually goes away. Then you also have a warming effect when you convert the forest to the grassland. And the roughness length actually, in fact, actually cools when the forest, but the inverse happens when it's converted to grassland, it warms. So the overall effect, what you see here is that if we have a deforestation in the higher latitude, you would expect the cooling effect, and in the tropics, you would expect the warming effect. So this is something quite interesting. You could imagine if tropics is deforesting, then you would have a warming, and if in the high latitudes are actually deforestation, then we have a cooling. Okay, so this figure shows clearly how much is the contribution over the latitude, and then this shows the contribution of individual component. The albedo effect. It's a cooling about 1.36 degrees Celsius. The evaporation actually has a warming effect about 0.24 degrees Celsius or Kelvin, and also the roughness has a warming about 0.3. So overall effect of the deforestation of the entire globe would have a cooling effect of about 1 degree Celsius. It's quite interesting. We always thought that maybe we'll have a warming. Obviously, warming is more dominating in the tropical region. Now, let's move on to my major, talk about how the climate is changing the land cover land use. I think it's not just talking about the climate, because the nutrients are the most important, actually, the component of the productivity of the plants. So it's actually very important to discuss about how the plants are impacting the land cover land use. In fact, the productivity particularly. And this is something what we have done in our research group. And I'm going to show some of our modeling work related to this topic. Then I will talk about how the climate is impacting the land cover land use. Okay, so what we have seen in the past, that the forest is cleared and the land is converted to the cropland. And if the cropland is abundant, then the forest regrow. Okay, we always thought that it'll come back to the same productivity level. But in fact, it does not happen that way, because plants also need additional amount of nitrogen. When you deforest the land over the time, the nutrients are lost, and the productivity of the plants goes down, because there's a limited amount of nitrogen remain in the soil, and that actually reduces the productivity. Okay, if suppose we deforest the land in another case, okay, and then again abandon the land, and then reforest, and then again abandon the land, cut the forest, and again reforest. So in these process, actually, a lot of nutrients are being lost, and the plants feel the nitrogen limitation. Even if the CO2 is being actually helping to plant productivity, but that productivity actually is reduced. So particularly about the secondary forest, okay, so we have also come up with this area of the secondary forest. We developed the secondary forest on a global scale, and these are some of the regions which are showing growing secondary forests on a global scale. So how these secondary forests are impacting due to the nutrients or the nitrogen. Okay, so I'm showing you two cases. One is, this is the secondary forest, and how the productivity is changing without considering the nitrogen, the nitrogen effect on limitation. And in this figure, I think it's not so clear, but also that some of the greening, which is green area, shows higher productivity, higher biomass due to the CO2 fertilization effect. But as you account for the nitrogen also interaction with the carbon, and what we see here in the higher latitude, for example, the productivity goes down, okay, because there's not enough nitrogen available to the plant, so the productivity goes down. So this is another important, actually, the feedback between the nutrients, carbon and the nitrogen. Okay, so another important thing is not only the above ground nitrogen, but also the soil release nitrogen under the climate change. I'm showing you an experimental result performed by Jerry Melillo's research group in Harvard Forest. What he shows that under the soil warming experiments, and he performed from about 10 years of experiment, and what he shows that as the soil warms, the nitrogens also released from the soil, and actually it increases in the atmosphere. The question is how it actually impact the plant's productivity. Quite interestingly, that minimal amount of nitrogen release, in fact, helped the productivity of the plants, and it increased the productivity. This is another interesting thing. Okay, so we have also done some experiment using our model, which I'm showing here. Again, only showing the effect of the soil warming effect and release of mineral nitrogen and how it is impacting the forest. And the green area shows that as under the global warming condition, that productivity of the plants, not for the entire globe increase, but particularly in the high latitude, we see much higher productivity. But in some region, you would see the red, which is the productivity reduced, and it is mainly because that plants are not only the nitrogen limiting or the CO2 helping the growth, but there are other limiting factors, for example, the water. So plants are co-limiting nitrogen and the water. So in some regions, nitrogen is not the limiting nutrient, some other factors, stresses like water is in limiting nutrients. That's why in these, some of the regions, in fact, actually the productivity goes down, even if the nitrogen is increasing from the soil. Okay, so just to show you the results in terms of the the latitudinal base, and most of the region here in this region, because these regions are the water stress region, so you would see that even if the mineral nitrogen is released from the soil, but still the productivity goes down. But in other region, in fact, actually the productivity goes higher. Okay, so now about how the climate is changing, the land cover, land use. There are a number of studies have been performed using satellites data, particularly, the data like NDVI, what we call the normalized, the difference vegetation index, which is a very important index developed based on the satellite data to provide the, how the phenology of the plants are changing over time. And the scientists have used this information to determine how the phenological changes are happening over the time. Phenological changes in terms of, the onset of growing season, end of the growing season, or the length of growing period, in fact, actually. So as we have heard, then high latitudes have a melting of ice. Climate is warming in the high latitude. It has a direct impact on the productivity of plants in the higher latitude. We see more greening, and this is the research done based on the satellite data, which I'm showing in this slide. And it is for about 30 years of satellite data using the NDVI, as I have mentioned. And what this study suggests that there is a lot of greening is occurring because of the warming occurring in the higher latitude. And the study actually suggests, not actually done a detailed analysis, that it's all about actually global warming, which is increasing growing season, longer growing season in the high latitude. And because of that, actually the shrub area is getting more denser, and the grasses are getting actually converted to the other biome. And that's why we are seeing the greening. There are other studies done actually on the same topic, length of growing season. As you could see, based on this study published in the environmental research letter, showing the red area in these regions, the length of growing season is increasing over the time, over the 10 years of time between 2000 and 2010. Another factor which also can impact actually the plants is the forest fire. Higher latitude is seeing huge amount of forest, particularly in the Arctic region and the middle part of the Canada. And that also is impacting not only the greening, but now we are also seeing the browning. That means the productivity is going down in this region, as you could see. So it's not only about the growing season due to the warming, but also the NDVI goes down. Okay, so it's very hard to say, is it because of the climate change or is it because of the forest fire? As I have mentioned, these studies have not yet looked at in more detail about the drivers of these changes. As I have shown you, it's not only about the climate change, but also the nutrients which are stored in the permafrost. As the permafrost is melting, the nitrogen is being released, mineral nitrogen, and that is also helping the productivity of the plants. So some of the productivity, what you see here is, or the greening, is not only because of the climate change, but also because of other regions like nitrogen. Another thing which I have not mentioned is quite interestingly, it's true that CO2 fertilization effect actually helped the plant productivity, but also there is a study published in actually Nature suggests the higher CO2 also helped at the growing season. In fact, it's quite interesting. Results is also that although the growing season due to the higher CO2 is actually getting longer, but the reproductive region time is showing much, is not increasing as much as it should be. So the conclusion of this study is that longer growing season is not due to the warming alone, but also a higher atmospheric CO2 concentration that can extend the active period of the plant annual life cycles. Second, elevated CO2 further extent growing, but not reproductivity season length in the warm grassland. This is particularly about the temperate forest area, and which shows that although the growing season have got longer, but the reproductivity has not gone that high. Okay, I'll skip this. In our group, we are also doing very same or similar study, but we are using a different approach. One of my students have actually used also the NDVI to come up with the phenoregions, about 49 phenoregions on a global scale. Phenoregions are the regions showing very same or similar properties of the phenology in certain regions and how they are changing over time. I'm not going to go in more depth. So we have done this over the last 30 years of time, and how the phenoregions are changing. We have looked at on a global scale. So one other important thing which I would like to also mention about how the drought is impacting also the plant productivity. And this is the research done by Zoe and Running from Montana, and they show that actually droughts are also impacting, obviously, the productivity. What I'm showing you here is the NPP trend, and the green is that warming, although it's actually drought in certain region, but the warming, as I have shown in the previous slides, helping the productivity, but in some region, in fact, actually it's reducing the productivity. In the next slide, I'm showing you the relationship between the NPP and also the net primary productivity, and also the Palmer drought severe index, relationship between that. And it clearly shows in both northern and the southern hemisphere, they have a quite good correlation. So it tells something that it's not only about the climate, but the droughts and also other factors can also impact the productivity of the forest. Okay, so how much is, are impacting these, the droughts are impacting the different plants. What this study suggests, actually done by you and published in ERL in 2006, and what they shows that how much is the recovery time for each individual plants, on a global scale, and it could vary depending on the plants between 30 days to about 120 days. And quite interestingly, this next figure shows the relationship between the average recovery days versus the GPP for different ecosystem. Quite interestingly, that the recovery time for the forest is much, much longer, in the sense that if the GPP of the plants is higher, then the recovery time is longer than the herbaceous plant, because the roots for the the forest is root are much deeper. They can go much deeper in the soil and actually take up some water. But the shallow roots plants actually takes much longer time to recover from the droughts. Just a couple of last slides. This is the research done by us, actually published in Nature, which shows that how the drought activities are actually delaying the recoveries from the droughts. And we just published this paper this year, and it shows that the recovery time is taking much longer due to the drought conditions. This figure shows the area impacted by droughts. How much is the recovery time for different areas? 6 months to about 24 months. And this is the total area. And these are the area, takes recovery time about 24 months to about 6 months. And as you could see, over the time from 1900 to 2000, the recovery time now the plants are taking much longer than it used to be. Okay, just to skip this, the two major conclusions of this study is that recovery is longest in the tropics and in the high northern high latitudes, and drought impacts have increased over the 20th century, as I've shown in the previous slide. But there's a prediction also about this study that if droughts become more frequent, the time between the droughts may become shorter than the drought's recovery time, leading to a permanent damage of the ecosystems. With this, I'll close my talk, and I'll be happy to any questions if you have, or maybe in the later.
Okay, thank you. Okay, I'd like to remind everyone that there'll be a panel discussion, plenty of time for questions at the end of the session. The next speaker is Dr. Daniel P. Schrag. Dr. Schrag is the Sturgis Hooper Professor of Geology, Professor of Environmental Science and Engineering at Harvard University, and Director of the Harvard University Center for the Environment. He also co-directs the program on Science, Technology, and Public Policy at the Harvard Kennedy School. His talk is titled The Timescale of Climate Change Impacts on Land Use and Ocean. Dr. Schrag.
Thank you. I'm going to take a slightly different perspective here. I am going to talk about land use a little bit at the end. And I think I know why I was asked to be in this session. Madhu and I have been working together for the last 5 or 6 years on a report that will still never see the light of day for the EPA on biomass and its use as an energy crop. But that's a story that we may get to in the questions. I'm not sure how much I'm going to talk about it here. I want to talk about timescales. Before I do, I want to mention, just as I'm beginning to talk, the winds from Maria are beginning to hit Puerto Rico. Puerto Rico is in big trouble. It's a Category 5 storm. It is the 3rd Category 5 storm this year. There have been 6 years since the 30s that we've seen 2 Category 5 storms, more than one. And this is the first time, I believe, that we've seen 3 in 1 year. I hope people in Puerto Rico are safe, but I fear that there's going to be a lot of damage there. It just hit Dominica with 160-mile-an-hour winds, and it's very nasty. So I want to talk about the timescales of climate change. And the reason I have an S there is that there's many different timescales in climate change. And to me, the timescale issue is really the one that makes climate change so challenging. You know, some people say this is the most important problem of our generation, and I actually think it's just the opposite. I actually think the reason climate change is so difficult is because it's never the most important problem. And it's because of long time scales. There are other reasons why climate change is difficult, like it's a global collective action problem, and that's another reason. But the time scale is particularly challenging because it's never more urgent than a North Korean nuclear effort, or, you know, it's always going to feel, even after a big storm in Houston, it's still going to feel like something that is a lower priority. I've been listening to talks here today. I always thought about this quote. It attributed to Niels Bohr, but apparently it's not really him. It's very hard to predict, especially the future. I think we should all have a certain amount of humility going forward. I've been seeing a lot of climate models and predicting what crops are going to do in 30 years in the future. And let me just remind everybody, this is an experiment we're doing on a very complex system, and we don't understand a lot. I've heard Dave LaBelle's stuff mentioned a lot. I think what Dave LaBelle's done is great. I'm a big fan. But at the same time, I think Dave LaBelle's probably grossly underestimated human adaptive capacity, and frankly, the ingenuity of farmers. If we had actually gone back 30 years and predicted what was going to happen now, we'd be completely wrong because of the ingenuity of farmers. So I think we have to be humble in our forecasting of the future. And remember, that doesn't mean we shouldn't do it. It just means that we should realize there's lots of open possibilities. By the way, those mistakes we make in forecasting can also go in the other direction. And climate change can throw some curveballs that we don't see coming. And every 3 or 4 years, I would say, I change my mind about what the biggest impact of climate change is going to be. And that's just a measure of how dynamic this system is and how complex this system is. Okay, so 3 different timescales that I'm going to talk about in climate change, and I'm mostly going to talk about the third. First is the carbon cycle. I'll just talk about that very briefly. The second is the timescale of the physical climate system, that is things like ocean heat capacity and the timescale of different types of climate feedbacks. And then finally, the timescale that I think people don't think about enough, which is the timescale of energy systems. and the time scale for change. And that's where I've seen a lot of naivete about the real problem we're facing here. And I think it's important to think about all three of these. Okay, let's start with the carbon cycle. I am a geologist, so I think about different timescales, including very long ones. And the carbon cycle timescale for climate change is much longer than many people realize. Currently, as most of you know, about 60% of our CO2 emissions remain in the atmosphere. About 40% are taken up by the land and the ocean. We call that 60% the airborne fraction. And about half of that airborne fraction will still be in the atmosphere 1,000 years from now. That's actually a lot when you compare it, say, to high-level nuclear waste. High-level nuclear waste, if you bury it 1,000 years later, about 1% will still be there. So CO2 is more persistent than high-level nuclear waste, just to put that in perspective. But a third of it will actually still be there 20,000 years from now. Okay, it has a very long time scale. So we are making decisions today that will affect the Earth, not just for your grandchildren or your great-grandchildren, but for literally thousands of generations of humans on this planet. They are going to be dealing with the consequences unless we develop a very cheap way to scrub carbon out of the atmosphere. Okay, that's one time scale to think about. The second is the time scale of the climate system, and there are many different ways to think about this. I've been heavily influenced by this paper by my friend Miles Allan from Oxford, where he did a series. He was really one of the first, but many people have confirmed this, looking at various emissions trajectories. He found the surprising result at the time that, in fact, the peak warming of the Earth was remarkably insensitive to the specific emissions trajectory. And really what it cared about was cumulative global emissions integrated over about 100 years or so. Meaning, if you ran many different scenarios where you emit more or less at different times over the century, the reality is that what the Earth really cared about was the cumulative global emissions. And I think we sometimes miss the point. People think that they're really, we really have to get our state's emissions down, or we have to get our country emissions down. We should care about national emissions. The goal here is global cumulative emissions. Cumulative meaning I don't necessarily care about getting emissions down 20% by 2020 or 2030 if it delays getting emissions down much, much deeper in the future. I care about cumulative global emissions. That is, getting global emissions to zero as quickly as possible. And I think that's partly understood. There's other long time scales in the climate system. We actually see this. This is the temperature record from NASA, from NOAA, from the Met Office in the UK. And you see this very strong pattern. Does this work? This strong pattern of decadal variability, right? So we had temperatures rise very steeply in the early 1900s, and then from the 40s through the 70s plateau, and then go up steeply. In fact, our predictability of climate on a sort of 10 to 30 year time scale is very poor, right? There are some ideas that this plateau is due to sulfate aerosols. My own view is that it has nothing to do with that. I'll just show you this really quickly. I think it's very compelling that it matches with the PDO, the pattern of oscillations in the tropical Pacific that's on a quasi-decadal period. Let me just show an experiment my student recently did. We're working on a paper that explains all of this with a physical mechanism for the PDO. This is a climate model that's run with essentially a permanent extra radiative forcing. Essentially, there's an additional 2 watts per meter squared at the top of the atmosphere added all the time so that if you ran it forever, the climate model would just keep warming and warming and warming. We ran it for 120, sorry, my slide here is cut off the time scale. This is 120 years. Okay, so this is just 120 years. This is not a simulation of reality. This is just taking a climate model, adding this warming effect at the top of the atmosphere, and letting it run. And this is the global temperature, and you see the variability inherent in the model. This next model, all we do is we add a very small heat flux fluctuation in the eastern tropical Pacific, just a few degrees along the equator and just in the eastern part of the Pacific. So a tiny, tiny fraction of the world oceans. We periodically take a little heat out or put a little heat in, which is a sort of way of simulating what we believe is this natural oscillation in the ocean circulation. And lo and behold, this is what the model does. So you run exactly the same forcing and you get this kind of variability. In other words, You give it a constant forcing, and the Earth responds in fits and starts because there are natural oscillations in the system. The expectation that the Earth should perfectly match the forcing is just a poor understanding of how the Earth actually responds. I think this is, again, one of the timescales that's important to think about. And what that means is predicting what the temperature is going to be 30 years from now is probably has less skill than predicting what it's going to be 100 years from now, ironically, because of this kind of decadal variability. Okay, the final timescale I want to talk about, and I think this is the one that climate scientists are least familiar with, partly because we tend to not think about energy systems as much. That's the job for, the energy engineers. And I think it's very important for people who study climate change to also be familiar with energy technology and policy, because it's fundamental to the problem. This is a graph showing world energy supply from 1800 to 2008. Just to remind you, the dominant source of world energy for the first half of that period was this green area, which is basically wood, biomass. And you see the growth of the Industrial Revolution with coal, and then oil, and then gas. The red is nuclear. The blue is hydro, which of course has been around for millennia, but it was tiny scale. What you're seeing there is really the large hydroelectric dams in the latter part of the 20th century. Let me just remind you that the steam engine was invented around 1786. So coal didn't surpass wood as the primary source of world energy until about the 1920s. So it took about 150 years for coal to surpass wood after the start of the Industrial Revolution. So there is a time scale information here. By the way, renewables, wind and solar, don't get their own field here. They're merged into hydro because they'd be too small to see. I just recently did another version of this. The colors are terrible. The student who did this for me, I think she was colorblind. But it's not her fault, though. This is the new version of this, and it needs more labels. But now you can see wind. Solar doesn't get its own, but wind does have its own field. Does everybody see that? Maybe not so well. Okay. If you really look, that's now you can actually, if you zoom in, you can actually see wind. Now, Justin Gillis will correctly point out that if you just looked at electricity, you would see wind and solar more clearly. They'd actually have a little bit of property on that graph. That's true, but again, the climate system doesn't care about the electricity generation. The climate system cares about cumulative global emissions. This is what the climate system cares about, and let's just say we have a long way to go. We made a lot of progress, but we have a long way to go. One of the, when people say, oh, the timescales of energy, they'd say, well, shale gas has happened so fast, it's changed everything. And it's true. Shale gas has been sort of miraculous in its timescale. This is the shale gas boom, where back in 2006 or so, it was pretty tiny, about 1 trillion cubic feet. Today it's roughly a third of U.S. natural gas production. It's quite extraordinary. It is amazing what has happened to the gas industry. Now, let me just remind you, though, that this didn't involve necessarily a massive new infrastructure. A lot of it was in places where infrastructure either existed or the infrastructure was essentially pipelines, not huge new power plants. The natural gas power plants that we have built, that started in the late 80s, and we've essentially increased the power capacity steadily from the late 80s all the way up until today. Last year, for the first time, natural gas power plants were not the dominant new construction of generating capacity. Wind and solar were together. That's a nice place to be. But the point is, it took 25 or 30 years to get there. So we've been building gas plants like crazy for 30 years, and the gas finally came online to supply them. Okay, so I think one of the things that I've learned from studying the energy systems of the world, and specifically thinking about decarbonization, that is complete decarbonization, not just how do you get to a 10 or 20% near-term goal, is that it's unfortunately sobering that it's going to be much longer than many people think. Deep decarbonization requires an array of new technologies that we don't have right now. For example, energy storage, advanced biofuels, synthetic fuels, et cetera, and new infrastructure. regardless of which technology you choose, which technology ends up winning, because we need innovation, and I hope there will be surprises, but whichever one wins, there's still a massive infrastructure. This isn't going to happen like the internet. Sometimes people describe this as if this is like information technology or telecommunications. It's much more complicated. Unfortunately, it just doesn't seem like it's going to occur in just a few decades. I teach a course where I force my students to design a low-carbon economy for the U.S., sector-specific quantitatively, for 2050. It's a very difficult exercise. And there's no right answer, but they have to really get into the details of what are the different trade-offs and what are the choices. One of the biggest challenges is that if you want to supply electricity to the U.S. with mostly wind and solar, even if you had perfect battery technology that was cheap, you still need massive capacity, right? So today, the U.S. uses about 500 gigawatt years of electricity per year. The timing of that is heavily in the summer, so you actually need much more capacity than that to cover the peak summer demand, which is over 1,000 gigawatts. But you need about 500 gigawatt years on average. You know, that's the total energy use for the U.S. For electricity. The problem is that if you electrify transportation and electrify industry and electrify home heating, you're probably tripling that electricity demand. And so it's not 500 gigawatt years, it's more like 1,500 gigawatt years. And if you want to do that with wind that has a capacity factor of, say, 35% on average, or solar that might have a capacity factor below 20% on average for the entire US, you're talking about unbelievable numbers, like 5,000 to 8,000 gigawatts of new capacity that you need to build to supply electricity for the US with wind and solar. To put that in perspective, that number, last year we set a record. We installed 10 gigawatts of new capacity of wind and solar. So when I say 500 years at current construction rates, that's what I'm talking about. Now, we can accelerate that. We can build faster. But when I hear people say we're going to be at a low carbon energy system in 20 years, I just feel like that's maybe a little bit too fast based on what I understand about the energy systems of the world. And that's actually informative about what the nature of the challenge is that we have to face. We're going to be dealing with climate change not for the next 20 years, but for the next century at least. This is a long, long pathway. It also, I think, affects the researchers in this room. You know, so oil prices are low right now, so biofuels isn't that exciting. But that doesn't mean biofuels isn't important. Biofuels is really important. Let me show you this cartoon. It's both funny and it's also sobering. It's one of my favorites. It's the whales having a grand ball, to celebrate the discovery of oil in Pennsylvania. This was from Vanity Fair in 1861. It's a great cartoon. It's also a sobering cartoon because it reminds us that, you know, in my state, the main energy industry in 1800 in my state was whaling. We didn't stop killing whales because we cared about the whales, right? Now, let me be very clear. I care about whales. Okay, this is a sustainability conference. I care about whales. But I do not believe that we are going to just stop using fossil fuels simply because of climate change. I do think in various places climate change will allow us to put policies like maybe a carbon price or various other restrictions that will be able to tip the balance. But in the long run, technology has to be developed that will ultimately be perceived as better. Better doesn't just mean cheaper, but cheaper is a big part of better. There are other attributes: cleaner, more convenient, less polluting. Electric cars are cool because they accelerate faster, you know, a variety of other things that might be great. But they don't make the sound that some people like. The Germans are not into electric cars, ironically, because they really love their internal combustion engines. But, you know, that is all cultural bias that can be changed. I think it's important to remember, though, that technology innovation is important. So given the caveat that I said earlier about predicting the future, I'm about to try to do that. I'm not going to make specific predictions because I don't believe that we can, given the kind of innovation that's required. But I will say that from my perspective, you can forecast at least that some things are going to come before others. And let's just think about, in a very simplistic way, the effort to decarbonize in terms of 3 phases. Okay, and I put timescales on here only in a very broad sense. Phase 1, which I think we're in today, is essentially about increasing the penetration of wind and solar, backed by mostly by natural gas. And this is, by the way, for the US. If we were doing this for China, it would look a little different. And we're seeing, and substitution of natural gas for coal. Remember, coal is still 30% of our electricity consumption, or production. So we haven't gotten rid of coal in any sense of the word. Certainly in Illinois, coal is still big business. But we're going to gradually see backing out of coal, increase in natural gas use, and hopefully increased penetration of solar and wind. In a few states, that penetration is high. California, Iowa, Texas. Iowa is like 35% capacity wind. Unfortunately, Iowa is not an electricity market. Iowa is connected to all the other states. And so, you know, counting Iowa as a high wind capacity market is not quite fair. I think what we're going to see is more and more renewables until it really becomes difficult to manage. I think phase 2, which I suspect is going to come in sometime between 2030 and 2040, will be continued expansion of renewables, but now dealing with deployment of storage to manage the intermittency, as well as demand management and other strategies, electrification of passenger vehicles, as well as electrification of heating and industry. One of the amazing things that people haven't talked about too much, that kind of happened quietly over the last 15 years, is that heat pumps have gotten cheap. I recently had to put a new air conditioning system on my house, and a little mini split air conditioning system, and this is for like a $1,500 compressor system. For an extra $30, it was a heat pump system, which is essentially does both cooling and heating, same thing. So that's how cheap it is right now. And I suspect gradually all over the country, when people put in their air conditioning systems, they will replace them with heat pumps. I wouldn't be surprised if people don't sell air conditioners soon. They just make the heat pumps. And what that means is you can turn the electric heat on when it's not super cold, and it's far more efficient than natural gas heat. It's about 3 times as efficient. Okay, I see I'm getting pushed off, so I'll finish up very quickly. There's a longer time scale, and obviously the further out you are, the more uncertainty there is. Things like carbon capture and storage for natural gas plants, because right now we still think natural gas is clean. As soon as you no longer accept natural gas emissions as acceptable for climate, then you have to do something about that, and it's going to be hard to replace. Industrial sources, cement plants, steel mills, still a challenge. And then the problem of biofuels, and that's what I really wanted to talk about. We're here in Illinois, ethanol central. We make more ethanol than anywhere else, including Brazil, in the US. But here's the interesting thing. We still measure it. This is a nice figure because most of the time when people see ethanol, they measure it in this unit, billions of gallons per year. In the oil industry, you measure it in millions of barrels per day. So here, all of US ethanol production is not yet 1 million barrels a day. Okay? To put that in perspective, back in 2007, we were a little over 20 million barrels a day. We dropped down when high oil prices were sustained for quite a while, and we're gradually coming back and approaching that 20 million barrel a day slot again. So as long as we're measuring in gallons per year instead of barrels per day, by the way, converting gallons per year to barrels per day is a factor of 15,000. So it's a big difference. And the challenge is that petroleum and the way we use it doesn't just go to gasoline. Electric cars do not solve the decarbonization problem for oil. Oil represents more than 40% of our total emissions in the US. And even if we electrify transportation, we're still going to have to deal with diesel fuel, jet fuel, among other things. And it's really hard to electrify freight. Maybe we'll bring trains back to this country and we'll have electric rail, although frankly there's a lot of towns across this country that don't want trains back. They've built bicycle paths on the train tracks. Hard to imagine rebuilding those train tracks. Maybe it'll happen. In other countries, though, this isn't true. So Indonesia and Malaysia dominate the world palm oil production, big business. They're growing lots of biomass, and I just wanted to put biofuels in the future in perspective. Again, I don't think this is going to become a reality in 2020 or 2030, but I think we already see a fight going on between those people who care about biodiversity and conservation and people who care about business, and interestingly enough, they may actually have climate mitigation on their side. This is a big factory. This is Pearl, which is Shell's huge gas to liquids factory in Qatar. It's about a $20 billion project. It's the biggest single project in the global oil industry, and it's gas to liquids. It's massive, massive plant that converts natural gas, which is kind of stuck in Qatar, into liquid fuels that they can ship in a tanker around the world. Shell's making a lot of money off this right now, although they were worried when the whole storm came over Qatar and support of terrorism. Can you imagine a biofuel refinery that produces 200,000 barrels a day? 200,000 barrels a day is still a moderate-sized oil refinery. I believe we're not going to be serious until we can actually imagine capital projects like this. But if you're going to spend $20 or $30 billion on a biofuel refinery, you're not going to put it in Illinois. And there's one reason, which is this thing called winter. You're going to put it in a place like Malaysia or Brazil, where you have year-round harvests and growing seasons, because the capital intensity of that refinery is such that you need to feed it all the time. And storing that much biomass for so much of the year seems like it's going to be very, very difficult. So I think the U.S. is still going to have a big role in biofuels development and biofuels technology, and I think Illinois is at the frontier of that. But I do think the future of the global biofuels industry, when biofuels starts to seriously play a role in displacing petroleum, is going to actually come in the tropics, simply because of year-round growing season. They just have more water, more sun, and they can harvest year-round, and that just makes it a huge opportunity. I'll just conclude by saying I do think we already see the seeds of this tension, that ultimately climate change, if we are serious about stopping the use of fossil fuels, it's inconceivable to me that land use won't go up. Our demand for land is likely to go up, and that's going to pit different elements in the environmental movement against each other. We're going to have the conservation folks already who want to discourage biofuel development, and people who care about climate change who say, wait a second, if we develop good biofuels and they displace oil, that's a good thing, isn't it? And it depends on what you care about more. Do you care about preserving forests, or do you care about stopping climate change? It's a terrible choice, and yet I think that's the situation we're in. I'll stop there. Thank you very much.
Okay, again, we'll have time for questions after the next talk, which I'll pull up. Okay, the last talk in this session will be presented by Dr. Brian Allan. He's one of our own. Brian is an associate professor in entomology at the University of Illinois, and his research combines interests in the ecology of infectious diseases, conservation biology, and the influence of global change on human health and animal health. Dr. Allan?
Thank you. Thank you for this opportunity to speak as part of this Congress. This is a great resource that has been now an annual event on this campus, and I'm truly honored to be a part of it. I'm going to be speaking about both current and potential future impacts of climate change on infectious disease. I am in the Department of Entomology, where I study vector-borne diseases transmitted by insects and other arthropods. And it's one example of where climate change is expected to impact human risk of exposure to disease. But to be clear, there are many different pathways by which climate change is likely to impact human health. Here is a slide prepared by our own Centers for Disease Control and Prevention, attempting to break into different categories the various health impacts that are expected to accompany climate change. We're seeing some of these in the form of severe weather and extreme heat. What I'll be focusing on for the purpose of today's talk are some of the infectious disease aspects of this. This includes water, which is an important medium through which humans become exposed to infectious disease. And I'll also be talking about changes in vector ecology, which is the context in which I study this topic. So I'll give just a brief outline of my talk. Where I'd like to start is with some of the early work that was done on the impacts of climate change on human health, a lot of which came from a sort of first principles perspective, trying to think about how changes in temperature and changes in precipitation will alter infectious disease transmission dynamics, which we already understand. I want to then segue into what we don't understand very well, which is that some of these infectious disease systems which exist in nature are highly complex. And we don't understand these systems well enough at this point to reasonably project what will be some of the impacts of climate change. And so one thing I really hope to promote is that we need more basic science just to understand these disease systems. And then finally, I think we need to already be thinking about how to adapt to climate change in the same way that many other scientific disciplines are approaching that concept. And whether some of those adaptive measures that are being undertaken already provide opportunities for us to reduce some of the human health impacts of climate change. So I'll start with some of these first principles concepts, and beginning, of course, with temperature, which is known to be a fundamental component of biological processes. One of the very first predictions related to climate change impacts on human health is that with warmer temperatures, we'd see faster disease dynamics. The pathogens themselves, as well as some of the organisms that transmit them, are expected to reproduce more rapidly at higher temperatures. And so if you run with that framework, albeit somewhat simplistic, it makes good sense then that you would expect higher rates of human disease as temperatures increase. Here, looking at several different mosquito-borne pathogens, which have to actually undergo development within the body of a mosquito, we see that as the temperature under which those mosquitoes develop goes up, so does the dissemination rate of the virus, meaning the number of mosquitoes who quickly become infected and able to transmit the virus to a new host. This led to some modeling work early in the study of climate change impacts on human health that provided some real insights that I think contributed to some of the next steps in the field. When people model infectious disease dynamics, often the outcome variable they're most interested in are changes in R0. R0 is the reproductive rate of a pathogen. The simple way to conceptualize it from an epidemiological perspective is if a human is sick, it's the mean number of people that person will infect, so the mean number of secondary infections. And for a lot of diseases that will be impacted by climate, these are diseases that have a particular seasonal signature, a time of year when they occur. Example from vector-borne disease would be something like West Nile virus. People get that in the summertime because that's when mosquitoes are active. And so that's when the biology is in place for the R0 of that pathogen to be greater than 1, and the pathogen will spread. Conversely, something like seasonal influenza is something that we typically think of as being associated with the winter season. But from a modeling framework, what you can imagine is happening following this blue line here is that you have periods of the year when R0 is greater than 1 and the disease will spread, periods of the year when R0 is less than 1 and the disease will head towards extinction. One of the predictions that comes out of this climate potential impacts of temperature on this cycling of seasonal R0 is that if you keep all other aspects of the disease system the same and you simply shift the dynamics up as a result of the warmer temperatures, you'll both have a higher peak transmission season, so where R0 will peak in any given year will be at a higher R0 value, meaning more people or whichever host gets exposed to the agent, but also that the seasons will be longer as well because you'll have greater periods of time where R0 is greater than 1 as well. And so some of the early predictions that proved quite helpful include that we'll not only see more transmission, higher rates of transmission of infectious disease, but for some of these seasonal pathogens, more extended periods of transmission as well. Disease system from which we can derive some of the first evidence of climate change impacts on human infectious disease are malaria, which is really well studied because it's had such a huge impact on human health since our beginning as a species. What you're looking at in these figures here are the change in malaria incidence over time. That top panel is the global prevalence of malaria 100 years ago. or at the beginning of the 20th century. This map is the global distribution of malaria at the end of the 20th century. And this hot and cold map at the bottom here represents the magnitude change between the two. In part, the story of malaria is a success story. We've greatly reduced the prevalence of malaria globally through a variety of measures, and so from that standpoint, we've improved human health considerably. But it's been one of the main subjects of interest for climate change research, in part because there are areas of the world that, despite this overall background decrease in in malaria prevalence, where we've seen really large increases in malaria. It might be hard to discern looking from a distance, but if you look at the East African highlands here, you can see some little spots of pink and red where we've seen malaria incidence go way up. And this is actually considered one of the early best examples of where we're seeing in present time climate change impacts on infectious disease transmission. The figure I'm about to show you here is for these highland areas of East Africa, the magnitude change in malaria incidence over time. And what you can see is that areas that were effectively malaria-free have become areas with quite high malaria prevalence. People who have worked in Africa, perhaps during this time frame, may be familiar with the rule that you can no longer follow, that if you were above 6,000 feet, you didn't have to take malaria prophylactics because the mosquitoes couldn't complete their life cycles at that elevation. That's no longer true. These malaria mosquitoes have moved up in elevation, and human incidence of malaria has tracked that. This may seem like a relatively small part of the world then to be concerned about this increase in malaria, but the distribution of humans in this landscape is non-random as well. As you move up in elevation, or in this figure it's measured in altitude, you move up in human population density as well. Anthropologists, in fact, think that this may be a signature of when humans had to settle in malaria refuges at high altitude to avoid malaria in the area that predates prophylaxis. And so there's large population densities at these high altitudes, particularly in high elevation countries like Ethiopia. And so as you move up in that altitudinal gradient, you gain many millions of people with each degree shift. The range of mosquitoes is expected to move up about 150 meters. You gain about 9 million people with each of those increases. So one compelling example of a change in malaria prevalence or disease prevalence as a result of climate change. Precipitation is expected to have similar impacts, and both floods and droughts can cause changes in infectious disease dynamics. This may be one of the greatest health challenges we'll face as a result of climate change. The World Health Organization estimates that over 1 billion people lack access to safe drinking water, and possibly as much of a third of the world's human population lacks access to adequate sanitation. That latter becomes particularly problematic during flood events, which, as we've studied, are becoming more common. Looking at background rates of waterborne diseases such as cholera and other bacterial diseases that are associated with flooding events, we see patterns associated with outbreaks of these diseases associated with rainy seasons. And as natural disasters are becoming more pronounced, such as the 2010 major floods that occurred in Pakistan, we're seeing big outbreaks of waterborne disease following these natural disasters. Similarly, looking at the occurrence of cholera, is likely native to Southeast Asia, and I think that's the part of the world people first think of when they think of cholera. But actually the highest rates of cholera in terms of the size of the outbreaks and the number of people affected occur in sub-Saharan Africa. And looking at long-term data sets for occurrence of these cholera outbreaks, risk factors all tend to be associated with flooding and contamination of water sources in association with flooding events. And so as we encounter more flooding associated with natural disasters, we can expect waterborne disease outbreaks to increase. In fact, we're seeing that now with Atlantic hurricanes as well. The worst strains of cholera were introduced to the Americas with the 2010 earthquake in Haiti. They've now become endemic, and we are seeing outbreaks of these most dangerous forms of cholera associated with hurricanes, most recently Hurricane Matthew last year. And with some of the hurricanes occurring right now, there are projections that we'll see more outbreaks of these waterborne diseases. As we move into thinking about vector-borne disease, the ecology has the potential to get more complex because there may be many species involved. Some vector-borne diseases just involve humans and say they're mosquito vectors, but others involve a variety of wildlife. And so you then have to also think about how wildlife will respond to climate change in thinking about the potential consequences for human health. Certainly, changing distributions of vectors is thought to be one of the main consequences of climate change, although this is also partially attributable to globalization and patterns in human commerce. Two of the most important mosquito species from a human health perspective are taking on a nearly global distribution in the modern era as a result of human movements of these mosquitoes to new areas. Aedes aegypti and Aedes albopictus collectively are responsible for vectoring dengue virus, chikungunya, Zika virus, yellow fever. So they're two of the most important mosquitoes on Earth from a human health perspective. And between them, they cover most of the tropics and subtropics, and their ranges are continuing to expand. Aedes albopictus is now here in Champaign County and is knocking on the door of southern Chicago. And so these northward movements of these mosquito species is also likely attributable to changes in climate. But the ecology can get much more complicated. I'll talk about some of the research of a PhD student in my lab working in central Panama, where there's a stark rainfall gradient across the isthmus of central Panama. This is the work of Aaron Welsh, who also has a poster here at this Congress, so I encourage you to take a closer look at her research during a poster session. It's a system where tick-borne disease is problematic, yet we know nothing or next to nothing about the ecology of the ticks that occur there. And so Erin has been conducting surveys across the Isthmus of Panama, where she has found that the species composition of ticks changes quite a bit as you go across the isthmus. And perhaps even more interesting, the phenology of these ticks, which has barely been studied previously, appears to be strongly related to climate as well. Looking at the relationship with rainfall patterns, we find some tick species are strongly associated with the dry season, other tick species are strongly associated with the wet season. In the absence of this kind of basic biology about these organisms, it will be next to impossible to model future impacts of climate on the distribution of tick-borne disease in this type of a system. I'll jump across the world to some work I'm doing in Kenya, also on ticks. And this is in a very arid, semi-arid environment of central Kenya, where precipitation is becoming increasingly variable in this system. And the kind of ecological research that I think we need to do is work that's possible in this landscape, because some forward-thinking individuals have established long-term experiments where we can look at not just impacts of climate change, but other ecological changes that are going on along with it. The image you see here is a field station in this part of central Kenya called the Impala Research Center. And across the Impala Research Center, there's this strong rainfall gradient. A colleague of mine, Jacob Goheen, established a long-term, large-scale experiment that spans this rainfall gradient, that manipulates access to these sites by wildlife in a way that recreates biodiversity loss that's occurring in this landscape. And so we can look at both how changes in rainfall and changes in wildlife composition that are occurring simultaneously could impact tick-borne disease risk in this system. This is accomplished through a series of electrified exclosures. As you can see in these images here, these things have to be powerful enough to keep an elephant from going through them. You will regret the day you bump into one yourself. I can say I've only done it once. I will never do it again. Here we see some of the results of tick surveys performed within this Uhuru experiment. In the background here, Georgia Titcomb, a graduate student at UC Santa Barbara who performed this research. And what we find here is an interaction between wildlife diversity loss in this landscape and climate change. So across the rainfall gradient, which you can see depicted across the top here from the wetter sites to the more dry sites, we see a general increase in tick abundance. And that's disconcerting because this is a region that's projected to become more dry over time, and so we think more of the region will look like these dry sites. But particularly the sites from which wildlife have been excluded, so the total exclusion plots, we see much higher abundance of ticks, including ticks infected with a variety of pathogens, than we see in those sites to which wildlife have access. And so this suggests that there's going to be this interactive effect, that the loss of wildlife diversity combined with increasing aridity in this landscape can increase tick-borne disease risk in a way that could affect the health of very vulnerable populations. So in an attempt to look forward, I want to think about opportunities that biologists can capitalize on for adaptation, because I think people in other fields, particularly engineering, are thinking very proactively about this. And so I want to take you to another area of research in my group, and this is work that we're doing supported by the Institute for Sustainability, Energy, and the Environment, looking at stormwater infrastructure here in the Midwest and how it impacts our risk of exposure to diseases transmitted by mosquitoes. So as you walk down the street, you likely walk past one of these storm drains, and if you're anything like me, you wonder where that goes. The answer is it leads into an underground sump, which is known as a catch basin sump. And in conventional stormwater infrastructure, it looks something like this. So the water pours in from the street, it's caught in this basin, it's connected to some kind of storm sewer via an overflow pipe. This works really well at capturing and retaining stormwater, and so urban environments are often full of these types of catch basins. The main health problem, however, associated with these is that these are ideal environments for mosquitoes to complete their larval development. You get a lot of debris in there, which makes it a very productive environment, a lot of food for the juvenile mosquitoes. And so as a result, municipalities have to invest a lot of resources in conducting surveillance. Here you can see somebody with a dipper checking a catch basin for mosquito larvae. And if the dipper comes up and looks something like that, that then results in municipalities in having to invest funds in treating those catch basins with pesticides specific to larval mosquitoes, or larvicides, in an attempt to try to control the mosquito production that occurs in these catch basins. It's been a problem in stormwater management probably for as long as humans have been performing stormwater management. But meanwhile, there's an almost tectonic shift taking place in how we manage stormwater in developed countries, move towards a variety of technologies that are often referred to as green infrastructure. These include things like green roofs, rain gardens, permeable pavement, rain barrels. And so we're really changing how we manage stormwater in large part in response to aging stormwater systems, as well as increasing interest in preparing for more variable precipitation under climate change. And so a postdoc working in my group, Andrew Mackay, realized that this was an opportunity to study the impact of green infrastructure on stormwater systems. One great example of a stormwater system, a green infrastructure system that's being implemented, is called an infiltration catch basin. It has the same basic design as a conventional catch basin, the main difference being that the bottom is permeable, and so it'll capture water during a rain event, but then allow that water to infiltrate back into the soil. And so I'll tell the fast version of the story, which is that we saw an opportunity to study the implementation of infiltration catch basins in a city in Illinois, the city of Aurora, which was implementing infiltration catch basins at a very large scale. And so we took advantage of this natural experiment to study what would be the impact on mosquito-borne disease risk. This project involved a number of very intrepid University of Illinois undergraduates, and the results are quite exciting. So what you're looking at here are before and after the implementation of these infiltration catch basins. In the before data, we can see both the conventional and the infiltration catch basins are performing very similarly, both in terms of their capacity to hold water and in terms of their production of mosquitoes. Following the implementation of the GI technology, the infiltration catch basin, we see that those catch basins are much less likely to hold water and much less likely to produce mosquitoes than our conventional catch basins. And so something of a win-win from this green infrastructural technology in terms of its capacity to reduce mosquito production from catch basins. We saw something similar with rain gardens as well. In the interest of time, I'll do the shorter version of the story. I see you there, Jeff. So rain gardens also tend to have catch basins associated with them. Interestingly, the catch basins still capture and hold water like a conventional catch basin would, but the water tends to be much cleaner, and so the mosquitoes that emerge from those habitats don't live as long. And so that's highly desirable from the perspective of reducing virus transmission, because mosquitoes have to survive a certain amount of time to be able to transmit a virus. So to conclude, we're seeing changes in infectious disease dynamics that are already occurring that are attributable to climate change. The potential for climate change impacts on ecologically complex infectious disease systems is considerable. We're working against time to have an understanding of the basic biology of these systems to try to get some baseline information before these changes occur. And I want to encourage fellow biologists to look for opportunities to take advantage of adaptation strategies that are already occurring in other disciplines. I think we can piggyback on some of these to try to find ways to incorporate human health planning in our responses in climate change preparation. And I'll leave you with a pretty picture of a rain garden. I'd like to thank iSEE and NIH for funding of this work, and thanks for being part of this session.
Okay, if the speakers in this session could approach the stage, and we'll have time for some questions.
So this is a question for Dan. Great talk, Dan. So my question is, given the time scale that you mentioned, that it takes, for carbon, that it stays in the atmosphere and so on, if we were to take action today, how long would it be before we could see any effect? And in terms of, the effects that we're seeing right now are probably caused by actions that, build up of carbon over decades or centuries. And so people are concerned about tipping effects and how we need to be. We're worried about what might happen in the next 2 or 3 decades. Is there something we can do to prevent that, or is that pretty much a given and we really need to be focusing on the long run?
So let me be very clear. The large sort of momentum, you can think of this as a system with just enormous momentum. Within the climate system, there are many different timescales itself. So land, for example, responds much more quickly than the ocean. We know that the land has warmed up on average over the last 100 years, roughly double what the oceans are. Right? We've almost hit 2-degree warming on land. We haven't yet globally. So there are a hierarchy of timescales. And one of the great challenges of climate change is that, in fact, in terms of doing something about it, if what you mean is reducing our emissions globally, this is why it's so difficult, because the fact is that things we change in terms of CO2 emissions, things that we change now are going to have a very minuscule effect in the next 30 years, partly because of the decadal variability. There's a lot already baked into the system. It'll have a modest effect 30 to 60 years out and a substantial effect longer than that. I still think that's plenty of reason to do something about it, but you can see why it's a difficult problem. Now, on the other hand, on the preparedness side, and by the way, we all, scientists, love the word adaptation. I think we're all Darwinists. When I was in Washington, I learned that adaptation is a bad word. Not because some people don't believe in evolution, which is also true, but because adaptation sounds painful. Do you want to adapt? That doesn't sound fun. But being prepared is a very positive thing. And think of the Boy Scouts and the Girl Scouts, right? Being prepared is a very good thing. So I think it's important to use words properly. In terms of what we can do now, that's why we actually wrote a letter to President Obama in 2012 and said the first priority is to focus on national preparedness. And as communities focus on preparing for the impacts of climate change, they will learn more about the risks and vulnerabilities, and the idea is that then they will be more likely over time to support action on reducing emissions as well. That was at least the thought. But honestly, it's very difficult. Now, if we're talking about some short-lived species, that's a little different. Or if you want to talk about solar geoengineering, which Gernot Wagner is going to talk about in the next panel, those things can work quickly. Reducing sulfate emissions goes the wrong way. Putting particles in the stratosphere goes quickly the other way. So there are things you can do that have short time scales, but the time scale of the carbon cycle is long. By the way, that's just for temperature. If we actually think of other impacts, like Justin Gillis was talking about sea level rise is an even bigger integrator, right, of the history. Ice sheets don't just respond to what's happening right then and there. The collapse, say, in Antarctica and the slow flow of glaciers represents the cumulative actions of what's happened in Antarctica over many, many decades. And so it's even more of an integrator of time.
This question is also for Dan. And during your presentation, you speak briefly about heat pump, and you said the benefit of heat pump 3 times cheaper than natural gas, and then also
3 times more efficient.
3 times more efficient than natural gas. And then we got your message. The time cannot wait. We got to do it as soon as possible. So it's 3 times more efficient, and then it can replace the air conditioning in the future. But also in your graph, there's no such representation of heat pump in your the graphic you shows. So what's the hurdle? What's the problem? Why are we not using it fast enough? Because based on DOE study in 2012, we are using about 40% of our energy for indoor heating, cooling, and water heating. So what's the hurdle here? If you can elaborate, that would be really helpful. Thank you.
So that's so part of the problem is historical. That there's, and this includes the construction industry, but also a problem with heat pumps. That is, 20 years ago, heat pumps didn't work when it was very cold. Thermodynamically, heat pumps do lose efficiency when it's very, very cold, but they're much more efficient than natural gas at 40 or 50 degrees Fahrenheit. When the temperature goes down to 10 or 20 degrees Fahrenheit, they get to be about the same as natural gas in terms of the overall efficiency of the system. So still pretty good. When it's really, really cold, they have a problem. I suspect the way that technology is going to come into our homes is likely as sort of a backup system. Many people today have both air conditioning and a separate heating system. Many have a forced air system that you can switch from heating to cooling. Well, essentially think of this now as a three-way system where you have an air conditioner that can either give you cold or it can give you heat with the heat pump, and you have a natural gas furnace for those days when it's really, really cold. I suspect that, for example, in my home, the next time I buy an air conditioner in Cambridge, we'll do exactly that. I think that's the technology that's going to come in. I think it's going to be a while before people give up altogether on dedicated heating systems like natural gas heaters, but I think it will come. I think you'll see it in places like New York City, where they still burn oil predominantly because of natural gas pipelines that are limited, and I think it'll be in many parts of the country that have slightly milder winters. But I think you'll see the technology eventually percolate. It just takes time. You have a housing stock turnover. You have a perfectly good furnace in your system. Why do you want to spend money to build a redundant system?
Yeah, just a quick comment. We do have a heat pump system in our house here, and the heat pump is what's used the vast majority of the year. Every once in a while, the regular furnace turns on. So.
Again, to bother you, this picture that shows the history of the primary energy sources, I'm afraid suggests an inevitability, but that's clearly not the case. You could also show a picture of the growth of armaments, for example, 70 and 80 years ago, where there was a dramatic change of industrial capacity of the world. We stopped doing one thing and we started building armaments. So given that it's the cumulative emissions that matter, if it were done better, it would have done quickly. Isn't the problem just to devise policies and motivations to put our energy in the direction away from the fossil fuels to renewables in some dramatic fashion? After all, we did do it with armaments.
I would say the analogy with armaments is unfortunately not a great one. And let me give you a perspective. I used to tell this story all the time because I thought it was hopeful and uplifting, which is the story of FDR in World War II, after Pearl Harbor. The State of the Union, shortly after Pearl Harbor, FDR promised that he would build some obscene number of tanks and ships and artillery guns and and jeeps and all this equipment, more than the world had ever seen. And people thought he was a little crazy. We just lost our Navy, right? or a big chunk of it. And he met with the heads of the automobile industry, mostly from Detroit, and they came to Washington and they said, Mr. President, we think we can provide 10% of what you ask, but beyond that, you would seriously injure the automobile industry in the US. And he said, gentlemen, you don't understand. We won't be building any automobiles in the US. And that's what happened between 1942 and 45. We essentially turned over our entire industrial capacity to making arms for World War II. That was a very special situation. I think it's perfectly fine to use that as an inspiration and analogy. Recognize that the cost of doing that was enormous. This wasn't using the free market. People who were making tanks weren't allowed to charge, or making steel for those tanks weren't allowed to charge market prices, right? This was command and control. It was absolutely not a capitalist free market system. People sacrificed, and we banded together and actually produced more than what FDR had actually originally targeted. If you put the scale of what we have to do for getting off fossil fuels, I just want people to be clear of how big this mountain is we have to climb. We could do it with World War II-like efforts. Of course, we don't have that same industrial capacity that we had then in terms of manufacturing. A lot of that has gone offshore. But let's think of this globally anyway. It has to be global. We're talking about World War II-like efforts globally, probably sustained for 30 or 40 years. World War II did it for 3. So is it possible? Yes, it is possible. But I want you to be very clear about just how big this mountain is we have to climb. And I think technology and innovation are absolutely critical, because it's a whole lot easier if everybody just wants to buy an electric car than if you're trying to force people to do it because of climate change. That's all.
Okay. One more question, I see. Okay. One more.
Brian, am I correct in saying one of your slides said when you exclude the herbivores, the disease spreads more? Can you explain why?
Yeah, sorry, I gave the quick version of that story, but the reason is that rodents and other small mammals increase in abundance, and they prove to be more important tick hosts and pathogen reservoirs in this system. And so those exclosure experiments reproduce background biodiversity loss that is occurring as a result of habitat fragmentation and persecution of wildlife. What you tend to lose are the large mammals first, and then what are left are the smaller mammals, which tend to increase in abundance. And in a number of systems, those are the hosts that tend to play a big role in tick-borne disease dynamics, and so you see more ticks as a result of that.
In Massachusetts, I've heard that there's a very strong anti-correlation between fox population and Lyme disease. Is that the same story, right?
Yeah, exactly the same story, right?
Population.
Yeah, so foxes historically would have kept mouse numbers in check, and so with the decline in foxes, we've had big increases in mice and big increases in Lyme disease as a result.
Okay. I'm going to take a 15-minute break, and let's thank all the speakers again.